Welcome back. So we are in the third video for Module 12. Now, in the previous two modules, we talked about what performance was when it came to programming. And we talked about three different basic tools to measure performance. Those tools focused on time. But I said we don't just look at time, we can also look at memory, because its performance is tied to resource usage. Not just how long it takes you to do something, but what were the costs associated with doing it? The cost of time, the cost of processing, the cost of memory, whatever the resource is that we're having to have tied up to do what we're doing. So in this third video, we're going to talk about code tracing, and we're going to apply it. And we focus on memory. Now, memory is a big deal, and we've got to worry about memory leaking and what a memory leak is. So a memory leak is something that happens when you've got unused piles of data. The data just starts piling up, and you forget to delete it because you're not using it anymore. I kind of think of it as the TV show Hoarders, where somebody's just saved things over time, to where next thing you know, they're blocking what we're doing, and they slow down the performance of the system. Now, when you think of the word leak, you would think, well, my bucket sprung a leak, the pool sprung a leak, the balloon has a leak where something gets out. When we think about memory leaks, it's conceptually it's different. Memory leaks we look at as something is being tied up in memory that we don't need to have there, and it just starts consuming memory or using memory that we really need to have access to. So it's memory management is what we really need to focus on. Now, Python manages memory allocations by itself. It's got its own memory manager, and that memory manager is responsible for allocations and deallocations on the private heap. Now, we think about a heap, everything's just thrown in together. A stack, things are ordered. So in this heap, we can go in and pull out what we don't need. If it was a stack, I would have to pull things out from top down. So heap allows us to pull out these things as needed from wherever they may be in there. And in essence, what we want to do is try to keep track of the memory blocks. And we're going to do that using a library or a module called trace malloc. And what it boils down to is trace memory allocation. How much memory do we have tied up at any given point? So we've got a method that we're going to use. It's called getTracedMemory, to get the current size and the peak size of memory blocks along the way. So we want to see, what are we doing with memory? Up to this point, we looked at what were we doing time-wise. How much time did it take to do what we were doing? With this, how much memory are we tying up? Now this memory, what kind of memory are we talking about? We're talking about RAM. We're not talking about the hard disk. We're talking about RAM. It's not something I have an unlimited supply of. And when I run out of it, everything comes to a very slow creep or potentially a halt. So we go ahead and import that trace library. From there, we'll bring in pandas. We may use that for, and we will use that later on, for data frames. We've got a different kind of data frame we're going to play with. That's a dask.data frame. We'll bring in one as PD, the other as DD. And then we'll also bring in a time functionality. And it's similar to our date time, but this one's just time. We're only worried about how long in time it takes to do something. So we're going to define 3 different functions. So this first one, we're going to start tracing. I was like, wait a minute, I thought you said we're going to start it and the first thing you do is stop. Well, there's a rationale behind that. And essentially what this does is you can't have more than one running at any given time. If somehow there was one still running, something happened or it was still allowed to run, I want to make sure that anything that's running stops before I start doing what I'm going to do. That's all that means. So we stop anything that may be going, say, hey, we're in it, we're doing this, and then we start. Now, let's see if this will play nice with all of these pulled out. There we go, run. So there's starting. Here's where we're going to get that traced memory that I talked about before, what the peak is. And then this will perform the calculations, the difference between the beginning and the end. So I've got those 3 different functions that I've defined. I go run this, and it's saying, wait a minute, we've got a problem, and it doesn't like my print. So I'll go ahead and I'll pull my prints out. At least the ones that deal with that one. Run it again and see if we're fine now. Let me do, had to do this already once, where I need to delete my runtime. Sometimes we'll have things caught up in our runtime, and it's almost like it remembers something I'd been doing before, and since it's remembering what I've done before, it's kind of stuck on that memory, and that's likely what it's doing with me here. So I'll just start fresh. We ran through that. Let's go ahead and run those. Let's see if this runs clean now. There, it went clean now. It's kind of funny, isn't it? I went through, did these, and it threw me an error. Boom. So now it ran through all those without a problem. Sometimes when we're dealing with collab or a runtime, and this runtime's been running, I've had it running quite a long time now, between when I built out this notebook and recorded the different videos. This runtime's been running for a while, and it's remembering things that I've done in the past that it said, wait a minute, I've got a problem. I can't go do this because I've already done it, or I've still got that running, or whatever it may be. So we started it. And then I checked the time. I created this list, printed the list out. What time was it when I got done? What's the difference between the two? And then what took place in memory. So we come look at it. Were we there or not? Nope. Yes. Here's that list. Here's let's see what we printed. Not sure what I printed there, if that's the sum. I have to go dig back and see what that specific number is right there. Oh, I said print end. That's what that number was the time right there. Print whatever was at the end. Here's the difference in milliseconds. And then here's the peak size in memory. So that's one way to go about what we went through. Can go back through here, get it started, and then we've got two values, and these things look similar, and they pretty much do about the same thing. The one, let me go, I think I've got it down below. So elapsed time and the peak size that it will provide back to me. Now, if we come down the next section, we go look at things that are in a list. And that's what we, in a roundabout way, did before, but with what we're going to do here, we're going to manipulate a list. I mean, two different ways that we're going to manipulate this list. The first way, we're going to take this list. It's 5 different items. And we're going to concatenate them together and store them in a string. So we have this string we create called S. It's empty. And then we're going to go through a loop and programmatically go through item by item and take that and add it to that string. Take it and add it to the string. So we're concatenating each item to that string. And then we print the string out. How long did it take to do that? So we've got a way that we can go through and programmatically create a string of words from the words that are in a list. And when we run it, here's how long it took in Python. Time elapsed, it says 3 milliseconds. Let's see how long it takes. Yeah, it's this was 1.3 milliseconds. And it all depends on what we've got going on in the system at any given point. How much RAM do we have free? How tied up is the processor? Whatever it may be. So these values can change over time. But now when I run it, it's almost half the time that it was before. And then there's the amount of memory being used at the peak. Now if I do the same thing, but instead of using a for loop to perform the task, I then do it using a join. So here's a function built into the string class that I pass it some list and it'll join those one by one to the string. Okay. Let's go see. If I run this now, which one was faster? Significant difference in speed. Is there a difference in the amount of memory that's being tied up? No. So I can see memory-wise what's taking place, and I can see the overall time elapsed to perform the task. One is clearly more efficient than the other time-wise, but when it comes to memory, no significant. At least, I don't think it's necessarily significant. But if we were talking about doing this in 1 million or 2 million iterations, it would add up, wouldn't it? So the last thing we're going to talk about in this video is going to be tracing a memory leak. We're going to use that same library, or the same module, the trace memory allocation one. And we're going to go through and we're going to create snapshots of what's taking place along the way. Display some statistics, we're going to compare different snapshots, and print out the trace along the way. When it's all said and done, we're going to display specific ones. Like we're going to display 10 largest. Yeah, I'm going to do the top 10. So those are just functions. I'll go ahead and run them so they're there when I need them. Now I'll come down here and I'm going to invoke them or call them with my memory leaker, using my memory leaker function. And this is going to cause the system to start stacking up things that we didn't need to really stack up or use. We could have just gotten rid of things over time. And what this boils down to, we've got things that are global that just get bigger, 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 or local to where when we're done, they go away. So this creates a fictional memory leak, or a man-made memory leak. So we'll go look at the top 5 stats grouped by file name. Which ones do we have? Top 10 stats. Top 10 stats, top 10 stats. If we go through and we get all the way down to the end, the biggest memory block, what happened, and how much space was needed, whatever it may be. 12 blocks. 391 kilobytes. So this would allow us to go through and see what took place over time. And like I said, I'm just dancing over this last part of it. But it's something that in the future, if you're deeper in this field, you'd have an understanding of, yeah, I've got tools that I can use to go tell me what's going on. Why is my performance crashing on me? Let's go see. Okay? So keep in mind what a memory leak is, what that snapshot does. The snapshot grabs your statistics at a specific point in time. Has nothing to do with looking at a hard drive. You may see a question on that. And we'll see you in the last module. Last module, we're going to be short and sweet to the point. We're going to talk about, well, here, let me do one more. We'll deal with a data frame. We did there with the lists and did a leak. Let's go look and see how this runs on data frames. So here's something we've seen before. I've got a CSV file out on my Google Drive and I link to it, and then I'm going to essentially bring that in. So my path is in the URL. I'm going to bring it in as a PD. See how long it takes to do. And then we're going to do the same thing, but now instead of a PD, we're going to do a different type of data frame. It's a different library. Okay? So I ran the first one, a pandas data frame, and that one took 744 milliseconds. This one took 1757 milliseconds and used a whole lot more memory along the way. Knowing that, if you had to pick from one data frame to another, one library to use or another, they're not all the same. And at least this allows us some tool to be able to measure what it is we're using and see, hey, is this really what we want to be doing? All right. Okay, now with that said, we'll move on to the last video.